In this video, we're going to be talking about definite integrals. So here's the formal definition of a definite integral, and there's a lot of words, but what's really important is that we've been working with this summation, and as a limit of something that approaches 0. It looks a little different than what we've been working on. It's something called a Riemann sum, which is not something you need to necessarily know for this. So we've worked with integrals like this before, and it's definite because it is the integral or the area under a curve from some x equals a to x equals b, or y equals a to y equals b, depending on the variable that you are integrating. And that includes the process of finding the lower limit and the upper limit, which we have discovered. We can take the limit as whatever that variable is as it approaches infinity. In this case, it says it approaches 0, and we can actually find the area under that curve. And something else that's important is that if the function is continuous on that interval, then that means that it is integratable, or it has integratability. So if we look at an example of using the limit process to evaluate a definite integral, so not in terms of n, but in terms of some interval from a to b. So if a is x equals -2 and b is 1 and the function is 2x, right, it'll look something like this with an n number of rectangles in there. We can apply the limit process that we've been working on in the last video, and you'll end up with -3, much like you would use with the limit process if it was n. But something to note here is because the definite integral is negative, it actually doesn't represent the area of the region. So if the problem with the last example is that the answer was negative, so it obviously didn't represent the area of the region, this brings us to the formal definition of the definite integral as the area. So f has to be continuous and non-negative on that closed interval from a to b, and then we can find the integral and use that as the area. And my hope is that this will make a heck of a lot more sense if we apply this using examples. So let's get to that. Something that I do want to share with you is if you are asked to write a definite integral, and let's say you have this graph here, you're given a function like 4x minus x squared, and you notice that it goes from x equals 0 to x equals 4, you can put that into a definite integral. So that's area equals the integrand from 0 to 4 of your function, so 4x minus x squared, tack on a dx because you are integrating in terms of x, because that's your variable, and that's how you would write a definite integral. So now let's start with a very basic set of examples that use basic geometry and the area of basic geometric shapes to actually find the area under a function. So let's say that I have this function y equals 4, which is a very boring straight line, from x equals 1 to x equals 3. So the wonderful thing about linear functions and integrals of them is that it produces a rectangle, and I very well know the area of a rectangle is base times height. So the base here is 2 times 4, so that tells me that the integral here, or the area underneath that function, is 8. So let's move on to something like slightly more complicated, and let's say that I have a function x plus 2, so that is another line, and let's restrict it by the x-axis and from x equals 0 to x equals 3. So what I did is I noticed that this bottom piece right here up until y equals 2 is a rectangle, and then the top bit is a right triangle. And I know the equations for the area of both of those shapes. So the area of the rectangle is 2 times 3, which gives me 6. And the area of the right triangle here is 1/2 times 3 times 3, which is 9/2. Put them together, and the area under this function, x plus 2, is 21/2. And here's another geometric figure for you, but this time, ooh, it's a semicircle. Getting real fancy up in here. So let's say that my function is the square root of 4 minus x squared, and I want to find the area under that curve from x equals -2 to x equals 2. And of course here I'm going to use the area of a circle equation, which is pi r squared. R is the radius, but I have half of a circle, or a semicircle. So that means that I'm going to have 1/2 pi r squared. So the radius here is 2, plug that in, and I get 2 pi. And here we have two important, if not kind of self-explanatory rules, but they're important to note. When you have an integral from x equals a to x equals a being the same value, the area under that curve is 0 because it didn't go anywhere. Another rule, when you go from x equals a to x equals b, and you write it from b to a, that is like writing a negative integral from a to b of that same function. So for example, if you are asked to find the integral of sine of x from pi to pi, the area under that curve is 0. And then this is one that we worked on a few slides back. So the integral from, of x plus 2. Now we did from 0 to 3. So from 3 to 0, that just means that it's the negation of the integral from 0 to 3 of the same function. And that one was 21 over 2, so we just negate that. So it's negative 21 over 2. And here we have the additive interval property, which is written like this. So if I have the integral of a function from a to b, and let's say that there's some point c in between, so something like this, so from a to b, you can add the integral of a to c and also the integral from c to b to find the entire integral. And an example of that that's pretty classic is the integral of the absolute value function. So remember, the absolute value function is actually two lines, so negative x and positive x, that are joined together. So if you take the integral of that from -1 to 1, you can even apply the same geometric shape rule that we were working with before. We just found the area of these two triangles here. So that's like saying I can take the integral of negative x from -1 to 0, right? So this line up till here, and then add it to the integral from 0 to 1 of positive x, which is this line right here, which gives me 1/2 for this triangle and 1/2 for that triangle. Put them together, and the area is going to be 1. And two more properties to throw at you that are also kind of self-explanatory is a constant multiple rule. So if you have some constant outside of a function, you can just pull that constant on the outside and then integrate that function. Also, if you have two functions, so let's say f of x plus or minus g of x, you can separate those two and take those integrals separately. So the integral from the same numbers, like a to b, of f of x plus or minus the integral from the same numbers a to b for g of x. So you can pull constants on the outside and you can separate functions with addition and subtraction. So if we work out an example of that, let's say that we want to evaluate this function, so this polynomial here that has 3 terms from x equals 1 to x equals 3, and let's say that we're given this information, which gives us each of the pieces. So the first thing that I do is I break up each term here under this integral. So I'm going to pull out the negative, and I have the integral of x squared, and then I pull out the 4 from the 4x, and I'm just left with the integral of x, and I'm going to pull out a 3 here, and I'm just left with the integral of 1, which is like this thing here, which has nothing, so that's like 1 times dx. And so all I do is substitute in my values of each of these integrals here. So this becomes -26 plus 4 times 4, which is 16, and minus 3 times 2, which is 6, and that all adds and subtracts together to give us 4/3. And two last rules for this video. So this is called preservation of inequality, and all that means is that, first rule, so if I have a function that you can take the integral of and it's non-negative on a continuous closed interval from a to b, all that means is that the integral from those two values from a to b of that function is going to be greater than or equal to 0, which should make sense. And then also, if you're comparing two functions, so let's say I have f of x and then g of x, and if f of x is less than or equal to g of x, meaning that g of x is like quote-unquote taller along the y-axis, that means that the area under the curves, so for f and for g, that just means that for the same a to b values, that your g of x, or whichever one is taller or greater, is going to have a greater area than the one that's shorter than it, which also pretty self-explanatory. All right, that's going to do it for this video. Thanks for watching.